Um, so I didn't give a title because I don't, I still don't know what my title is. It's just called Minicourse. Um, but this morning I figured out what it is I wanted to say. It took me a little while to figure out what the story is, but here's the story. So the story is the following. So you're interested in a collection of sort of geometric objects of some variety, some sort of geometric objects. So these things can be, well, they could have very little geometry if you like. They could just be like things like topological spaces. Or maybe you want to do something more sophisticated and you want to work with manifolds. Or maybe you want to work with certain kinds of algebraic varieties. Or maybe you want to work with things like schemes. Or maybe you want to work with things like formal schemes or things still. Diamonds, I don't know, whatever, all kinds of fancy things that you can imagine thinking about. These are things that have some sort of geometry attached to them at some level. And then what we think about as homotopy theory, we think, okay, well, if I have a geometric object, then I can associate that geometric object, its homotopy type, and that's some sort of lossy procedure. That's some sort of lossy procedure that throws away a lot of the geometric information, but sort of preserves somehow some kind of shape information about the geometric object that we're talking about. Maybe in homotopies. Are we going to try and get away with it? I'll try. See how long I can make that happen. What I'm going to talk about today is I want to try to describe how actually there's a whole range of kind of intermediate things between these two extremes. And at various stages along the way, you might actually want to sort of look at information that is more than just the homotopical information, but is not as much as the sort of outright geometric information. So for example, maybe instead of thinking about a manifold, and maybe instead of thinking about that manifold's homotopy type, you want to think about something that somehow sits in between those two extremes. Because the question is, how do you do that? And well, no, that is the question. How do you do that? So let's see if we can figure out how to do that. By the way, it would be best for me if this were a conversation. I don't know everyone in this room, so if you have questions, please ask them, and that will help me understand like how much I should or shouldn't say about various things. So if I say something that you haven't heard of before or want to hear more about, just tell me to tell you more about it, and I will.
Clark gives the best answers to questions.
That's way overselling it. So okay, so let me start with some place that I hope is kind of comfortable for people. So I want to start off with just a topological space. So X is going to be a topological space. And then I'm going to attach to this topological space a category. And for now, you can just think of this as the ordinary category of sheaves of sets on X. If you like fancier things more, you're welcome to think of this as the infinity category of sheaves of anima. That's what I prefer to think about. I will just totally be sloppy and say category when I mean infinity category. So if you have a question about which one I mean, it's probably infinity category, but free to ask. So the question is, how reversible is this procedure? So I take a topological space, I extract its category of sheaves, and your question becomes, well, to what extent can I recover the topological space from the category of sheaves? And not just to what extent can I do it, the question is also, how do I do it? You know, how do I make that happen? And well, there's an answer to this question, and it goes like this. So if I have a topological space and I take an open subset of that topological space, so I'm going to start introducing some notation here. So I'm going to put a little circle. I learned this notation from Peter, who's here. For open subsets, I like writing them like that. The closed ones I'm going to write with a little slash, but I don't need them yet. So I'm just going to deal with this open one. If I have an open subset, then what I can do is I can look at the sheaf that's represented by that open set. So this is the thing that says, well, its point if V is contained in U and it's empty otherwise. Right, and so this is a sheaf, and it's a sheaf that you can get for any open set, right? So for any open subset of your topological space, I can write down a sheaf. And now this object, so this is an object, this yo-u is an object of the category of sheaves on X, and it's not just any object. It's kind of a special object because, like, it's not very big, right? It's quite wee. And well, what does it mean to be wee? Well, what it means is that this is an example of a -1 truncated object. So what does that mean? Well, that means that if you look, for example, at the diagonal map, oops, here, it's actually an equivalence or an isomorphism. This thing is its product with itself. It's its self-intersection, as it were. And see, the point is that inside of topos, which is the kind of category that sheaves are, inside of topos, you can sort of form fiber products. Those fiber products sort of generalize intersections. But there are some things that have self-intersections, right? For a typical object, it might have lots of self-intersections because you can cross things with themselves and get something new. But these objects don't have that property. If you try to intersect them with themselves, they just recover themselves. So nothing really happens. Another way to think about this is that this is a sub-object of a terminal object in the category of sheaves. It's a sub-object of the terminal object. So I have some procedure to take the opens of my topological space and produce, well, not all kinds of different sheaves, but the -1 truncated sheaves. So I have some sort of operation that takes opens and turns them into -1 truncated sheaves on X. And you can see, I mean, it's not too hard to see that this is a perfectly functorial operation in the sense that if you have an open, if you have an inclusion, U to V, then, you know, you got a map here going like that. So this is really a functor, you know, this is really a functor. Okay, well, let's think about what kind of category this is, this category of -1 truncated things. Well, so let me say some technical things now. So if you look at the whole category of sheaves, this is an example of what's called a topos. How do people feel about this word? And here I mean infinity topos, but how do people feel? Okay, that's a bleak look. Some happier looks. Okay, all right. So there's some varying experiences of this category. So what kind of thing is a topos? Let me just tell you really quickly what it is. So first of all, it's a presentable category. So that means that it has all limits and all colimits. And there's a small subcategory of this thing that generates the entire category under kappa filtered colimits in the sort of canonical way. So the way to think about these presentable categories is that they're big categories. They're the big boys out there, but they're controlled by a small subcategory. But the game is that you never specify, or you try to avoid specifying that small subcategory because it's kind of like choosing a basis. So you don't want to necessarily choose it all the time. So you just think about the vector space itself. So it's that kind of category, but it's more. It satisfies a descent condition. So the descent condition goes like this. I'm going to call this scripty X just for a moment. So the descent condition goes like this. Well, I can write down a functor. I can write down a functor from X to categories that carries U to objects over U. And if I've got a map, maybe I shouldn't call this U because that was the name for my open. I'll call it F or something. And if I've got a map here, well, sorry, maybe I want to do this from the opposite just to get this right here. Yeah. I think I'm making a mistake already.
You're doing it right.
What's that?
You're doing it right.
I'm doing it right. Then I want to take the pullback along this map. This thing preserves colimits? That's weird.
Yeah, it should say when you slice over a colimit, it's the limit.
It's the limit on the category. Okay, good. Thank
So
you.
it sends colimits and
Thank you.
limits and exop to limits and categories. So colimit.
I rely on Peter to get all my ops control. It's always been this way, right? I mean, if they were a PhD student, I was relying on them to help me get my ops correct. So it's happening again. So right. So what's the condition here? The condition here is that this thing carries colimits in X to limits of categories. So that's what a topos is. What a topos is. And the category of sheaves is an example of such a thing. All right, so let's think about what that means for this category, because this is a subcategory of my category of sheaves. Right, so let's think about what implications that has. Well, if you think about it for a second, you think about the category of these -1 truncated sheaves sitting inside this full category of sheaves, then what you realize is that this is actually it's a nice localization of this category of sheaves. There's a functor going backwards, which is the -1 truncation. The left adjoint to this thing. All my left adjoints live on the top in my conventions. So there's this sort of reflective property of this subcategory. And this this implies the fact that this is like kind of accessible and you've got this reflective property. This implies that this is a presentable subcategory. So it's a presentable category itself. Okay, but it's more than that. It's also just a poset. Because after all, if I have two of these -1 truncated objects, then you can check that in fact there can be at most one map between them. By that I mean that if you look at the mapping space between two objects that are -1 truncated, then this thing is either empty or it's contractible. The space of maps is either empty or it's contractible. So this is a poset, but it's also a presentable poset. Okay, but it's not just that, because you also have this kind of descent condition. And you can unpack what that descent condition means on this localization, right? This isn't just a presentable category, it's a presentable category with this descent condition, and you can kind of unpack what that means for this thing. So let me give you a little exercise if you've never done it before. Oh, it's good. Let me give you an exercise if you've never done it before. This category of -1 truncated objects is what's called a locale. So it's a poset with all soups and also therefore all infs. Such that there's a distributive law that holds. It's an infinite distributive law. And it says that, well, so for I'll use the intersection symbol for the infs and the union symbol for the soups so that it feels like the opens of a topological space, which is the example to bear in mind. It's this kind of thing.
You switched to script X. Is this true for any topos?
Yeah, this is true for any topos whatsoever. All I'm using here is just the fact that X is a topos. It doesn't require that you know that it sheaves on anything. This is this is a general fact. And that's something I want to thank you for bringing that up, because that's something I want to emphasize here, is that this is a sensible thing to do with any crazy topos that you write down, right? This is quite a general object here. And I still get one of these things called a locale. Of course, the other place where you get locales, which I already kind of mentioned casually, is the set of opens of your favorite topological space. So we have these two different locales, the collection of -1 truncated objects of a topos and opens in a topological space. And how do these answers relate? Well, you know what I'm going to say. This is actually an isomorphism of locales. This is a poset map that respects both unions and intersections. And it's actually an isomorphism. Okay, so our starting question was, suppose X is a topological space. To what extent can we recover X from its category of sheaves? What I've just done is I recovered the lattice of open subsets of X from its category of sheaves. Now you have to ask the question, to what extent is that the same thing as recovering X itself? I have answers for that too. Are there questions so far? Am I going too slow? Am I going too fast? People are more or less happy.
This board,
What's that?
move down this board.
Oh, for a second.
Is it okay to explain what the truncation map is? Sheaves to -1 truncation. If you can do it quickly, then. Up to.
Yeah, so so if I think about just the category of, in general, it's some abstract thing, but if I'm thinking explicitly about the category of sheaf, then what I'm doing is I'm taking F and I'm carrying it to the sheaf that sends U. Well, U gets sent either to the empty set or to the 1 point set. And that just depends on whether or not F on U is empty.
Okay.
So if F on U is empty, then you do this one, and otherwise you do point. Yeah.
Yeah, so I've seen the definition for like topos is for like an elementary topos, which is complete, co-complete, sub-object classifiers, and then the definition of like a Grothendieck topos, which is like the Grothendieck topology, like sheaves on a Grothendieck topology. How does that definition relate to like which one of those is that? Or
So that's a good question. So this is the Grothendieck topos thing. I will caution, however, that in this world, it is not the case, right? It's not just not known to be the case. It's actually not the case.
Yeah, yeah.
And I mean, yeah, so it's not true that all topoi are categories of sheaves. Even if
Yeah, it's not no. It's
That's
expected to
just
be
not known.
false, but
that one's just not known.
sorry, I thought you were going to say something else. So my
Oh.
prediction of what
Sorry, I
you were going to say was wrong.
was asking you if you could just predict what I was going to what the answer is. Both my questions and my
That's because we're working sheaves of anima.
Yeah, that's because we're working with sheaves of anima. So in the circumstance that you were thinking about the one categorical notion of a topos, and then you're exactly right. Like if I think about sheaves of sets, or sorry, if I think about a one topos, then that is always sheaves of sets on some Grothendieck site, just as you say. But in the infinity categorical world, that turns out, well, probably not to be true. And in any case, like if it is true, it's probably not true for a helpful reason. Like probably the site that you cook up is probably something crazy relative to what you actually want to be thinking about in some certain circumstances, which we will maybe talk about. Yeah. So, but right. And so the elementary topos thing, that might not be co-complete, right? Those elementary topoi things, they don't necessarily have all co-limits. Depending on what conventions you use. But if you think about what are called Levere topoi, those show up in logic and things. So, but I'm really only just going to talk about the presentable version with all the co-limits and limits and stuff. I'm going to avoid elementary topo. Do you have a comment?
It's also relevant to mention my alternative mind reading of you, which is, so if you state this condition one categorically, you don't actually characterize one topoi. You characterize the terminal category. And the reason is like this is really an infinity topos theory condition, and there's a version of this for one topoi, but it only works for those colimits that if you computed it in the corresponding infinity topos would turn out to be sheaves of sets.
Ah,
So like
Okay, right.
this we don't normally see as a condition for one topoi, but it's a huge advantage of infinity topoi that's not true like this for one topoi.
Thank you for saying that. Yeah, that's a very good point. Yeah, that's right. So this is really, did everybody hear that? Did everybody hear that? So this is really, I mean, I'm really using, this definition is only valid for infinity topoi. It's not true for one topoi. And yeah, you can fix it up to make it true, but it's just, you're not going to be able to do all colimits to limits. You can only do those colimits that are, that sort of stay in the one categorical realm.
Yeah, but you can just state it as it is in the infinity.
You can just state it as it is in the infinity case. So, yet another reason for us to, stay with infinity categories, right? As if we need more reasons.
Sorry for the question.
Yeah.
Interrupting, but does everybody but me know what an anima is?
Does everybody know what an anima is? So this is this thing that happened. I wasn't like really awake for this part. I don't know that. So for ages, we call homotopy types like just spaces. And that was already good. But then, so one of the things that happened was that it turned out, and we'll actually come to start talking about this, and Peter will talk about this more in their talk. So these spaces, right? These are what we might just call homotopy types. So this is the
Puppies.
called homotopies apparently. For years we just called these things spaces, right? And so we have this infinity category of spaces. But then what happened was these things have like homotopy groups. And what happened was it turned out there were circumstances where those homotopy groups themselves had topological structures that you wanted to keep track of. And so depending on who you were, you might try to make that happen by passing to some sort of condensed formalism, which we'll talk about a little bit. But that meant now there's like kind of two sort of directions that are kind of topologically. And so you kind of want to specify, oh, like what do you mean when you say discrete? Do you mean homotopically discrete or topologically? It starts getting confusing. So this is Clausen and Schultz's fault, I think. They started moving to anima, which I don't think they pluralize correctly. So like this is the correct pluralization, I think. But anyway, whatever. Or we could call them souls. That would be good too. I mean, I think the idea is supposed to be that when you have a category, one category, then you can kind of make it homotopical by adding in sifted colimits in a particular way. That's sort of a canonical construction that you can always do. So if you've got a one category, like the category of sets or the category of abelian groups, you can make it homotopical by adding in sifted colimits in a formal way. And when you do that, you pass from the category of sets to the category of animi, whatever. And when you think about the category of abelian groups, what you extract is the non-negative derived category of abelian groups. So yeah, so that's where this language comes from. This is this idea, that process. I was getting to a point. That process is called animation, which goes back, I think, to Baelen's, that name. And so you're supposed to kind of
Are you sure it's a plural? Isn't it just animated set? That's just short for that.
Oh, you want it to just be animated set?
Isn't this what it's just short for? No.
I don't know.
That's what I understand.
Like I said, I wasn't waiting for this bit. I was resting. So at some point during COVID, I didn't notice. Right. Why was I talking about? Why did you want me to say that, Mignon?
I just didn't know what it was.
Oh, okay. Well, that's what it is. That's what it is.
And this from an infinity cube.
These form an infinity category, that's right. And I mean, for a long time, I called these complexes because I was thinking about them as provided by fiber and simplifical sets in a very like kind of concrete way. And sort of over time, we've somehow kind of abstracted away from these sort of concrete things to this sort of fun world over here. But it still means the same thing. We're still talking about the homotopy type of spaces. You have a question? Yeah.
I have an expert to ask this question to.
You mean Peter?
Is it correct to say, if I say anima, it's implicit that I mean an infinity category of spaces? Whereas
Yeah.
if I say spaces, there's this lingering ambiguity that I might be thinking of a model category or a one category.
You said that much better than I could. Yeah, that's exactly the issue. Yeah, precisely. Yeah. And also this lingering issue of once you get into condensed things, whether or not like what direction is the space direction now, and that starts to get a little fuzzy. Yeah. Further questions? Yes.
For your definition, animation is synonymous to like stabilization, right? That's the same thing.
It's not stabilization, it's just adding in the sifted colimits. So I'm not, like, these things are producing positive homotopy, but they're not producing negative homotopy. If I stabilize, then I'll start producing negative homotopy. So yeah, so for example, if I do this with abelian groups, I don't get the whole unbounded derived category, I just get the stuff in non-negative homological groups. Other questions about the game we're playing? Okay, so what was I going to do? I was going to do something. Oh, right. I was going in a different direction. So we have this infinity topos that we have gotten from this topological space. Then we looked at the one truncated objects of it, or the minus one truncated object. We could also look at the one truncated objects, but those would be the sheaves of sets, I guess. We're going to look at the minus one truncated objects of it. Those minus one truncated objects form a poset, in fact, a really nice poset called a locale. And that locale is actually isomorphic to the lattice of open subsets of our original topological space. Okay, so we can then ask, well, which topological spaces can be recovered from their lattice of open sets? Who knows what the answer is? What's the magic word? Sober spaces, yeah. We're going to talk about sobriety. So, to tell you this story, maybe what I'll do is we'll just talk about what happens here. So we're going to take topological spaces and we're going to turn them into locales. By the way, we're going to be talking a little bit about locales in some of the later lectures again. So that's why I'm kind of talking about them so much now. And let me just emphasize that the maps here aren't quite what you might think they are. If I have two locales, L and L prime, then a map of locales from L to L prime is a poset map from L prime back to L. So if this is called phi, then we usually call this one phi upper star. And we require that this thing preserves all sups and the finite infs. That's a hard thing to say. All sups and finite infs. And so this is just so that we can say that this is a functor. This way of taking opens out of a topological space. So we take a topological space, we extract its lattice of opens, but of course, it's not the image of an open that's an open, it's the pre-image of an open that's an open under a continuous map. So now this map is covariant rather than contravariant. And since I obviously have trouble with ops, it's better to do it this way. All right, so this functor has a right adjoint. I shall tell you what it is. Maybe I'll give you an exercise to think about if you've never thought about these things before. So what you can do is you can extract from any locale a topological space in a canonical way, in a universal way, in a way that is right adjoint to this functor here. And what is this operation? Well, so if I take my favorite locale, I guess I'm calling these L now. If I take my favorite locale, L, then what can I do? I can look at the HOMs in the category of locales Well, from the point locale, what's the point locale? Well, it's like the lattice of open sets of point into L. This is a set, and you can topologize it. Maybe I'll have that be part of the exercise, unless you insist that I tell you precisely how. But let me just emphasize what this means here. So this means that you're taking your locale, right? So this is a post set with a bunch of stuff, and you're interested in maps to this set right here. These are post set maps, and they have to, in this post set map has to preserve all sups and the finite infs. We'll have trouble with that word infs, right? That's what this set is. You all happy? But you see, the idea is that, well, if I have a locale and I want to sort of like see what a point of that locale should be, which is what this kind of operation is trying to produce for me, then I want to be able to look at the space of maps from the thing that is the point in the world of locales, so opens of a point, to your locale. So that's what we're going to do here. You have a question? No. You were giving me a look that I felt like was suggestive of a question.
I'll look at someone else.
I understand, like, so given a point, so such a map from L to this opens of points, should I think about this of specifying which opens contain that point?
Yeah, exactly. Thank you very much. That's right. So when you think about this, like, how should you be thinking about this as a point? Well, like, I'm singling out some collection of opens, as it were. If you think of this as a collection of opens, I'm singling out some collection of opens by doing this. Which collection am I singling out? I'm singling out the collection of those opens that contain my point. And this is important because, well, you might not have that many points, actually. You might have a lot more opens than you have points in a general locale. Locales can have lots and lots of opens and not very many points. And that's exactly why this adjunction here isn't going to be an equivalence of categories, right? In fact, let's think about the extent to which it is an equivalence of categories. Well, what can I do? If I have a topological space, then that will receive, no, it'll go to the category, to the space of points. I didn't tell you what the topology is here, but it's uniquely specified by saying that this is the right adjoint, but I could tell you more. It goes to this thing. This is the co-unit, or no, sorry, the unit. Ops. So we have this perfectly nice continuous map of topological spaces. And this nice continuous map of topological spaces is not in general a homeomorphism. But it's kind of not off by very much. It's pretty close to being a homeomorphism. What I mean by that is the following. So, so this thing, I'll write words here. This is a homeomorphism. If and only if. There's no real problem with this thing. Like, if this were a bijection, it would be a homeomorphism. That's not where the problem lives. The place where the problem lives is the fact that there might just not be enough points in open of X. And so one way to say that is it's a homeomorphism if and only if well, I'll say it like this. Every irreducible closed subset Z of X. So these are closed, so I'm going to use my notation. So what does irreducible mean? Irreducible means that you can't write it, it's non-empty, and you can't write it in an interesting way as a union of two smaller closed subsets. So if you're thinking about a Hausdorff space, you're thinking that never happens, and you're right, right? So you just don't have that many irreducible closed subsets in a Hausdorff space, they're just points. But if you're thinking about something more exotic like a scheme, then you're talking about things that look like, irreducible schemes. Things that don't do this kind of thing. Anyway, so you're thinking about these irreducible closed subsets, and what you want to say is that every irreducible closed subset has a unique generic point. Or actually, in this case, I can say, well, yeah, say it has a unique generic point. So that's a point eta in Z, such that eta, it's just that Z is the closure of that point. So in the Hausdorff case, we're already done because the only irreducible subsets of irreducible closed of a Hausdorff space are just points, so nothing's really happening there. But if you're talking about it, but this is more general, right? This is a more general. So this is the condition of sobriety.
What can you say about the co-unit?
Yeah. What indeed can we say about the co-unit? Let's see. So with the co-unit, I'm starting with the locale. Starting with the locale, I'm taking its collection of points, and I'm taking the opens, and I'm mapping that back to L. So, well, okay, so this is an isomorphism. I'll give you the characterization of when this is an isomorphism. That's, I think, all I know how to say about it in general. This is an isomorphism if and only if. Again, it's kind of an enough points sort of situation. So what is it going to mean here? It's going to mean that if U and V are elements of L and they are different, then there exists a point. So that's a map of locales from open of a point to L. So that's a map of cosets called, I didn't give it a name, I'll call it X upper star from L to this thing. And so I need a point that knows that these two elements of my lattice are different. Right? That's what I need. I need a point that knows that U and V are different. And so that means that I need to see that X upper star of U is unequal to X upper star of V.
This is kind of the minimal condition.
Yeah, you ask for like the first thing. It's great because you ask for the first thing you think of that you will need, and it turns out to be sufficient to get this thing to be an isomorphism. So this is the condition for a locale to be spatial. The spatial locale. Yeah.
Two questions. One, is this unit map always surjective?
Yeah.
The second question is like, maybe not so important, but we have space and -1 truncated like on the same board here. I get uncomfortable. Are there like choose an arbitrarily big N?
Yeah.
Are there spaces for which the -1 truncation of the sheaves on X, the -n truncation of sheaves on X is like trivial?
So
I don't like -n truncating sheaves on X. That doesn't make sense to me. I mean, I know what it is, but like I can't tell like when this should be interesting or not.
yeah, so I mean, we're talking about sheaves of spaces.
Yeah.
So we're really only, I mean, so like, let's leave the sheaves out of it for a second. Let's just think about spaces themselves. Right, so you can talk about, spaces whose homotopy is concentrated in degrees less than n. We all know what that means. This -1 business, this sort of negative thinking, here we have the category of sets, right? So these are the spaces that don't have any higher homotopy whatsoever, right? And then I'm saying that there's an even lower down thing, which are the -1 truncated spaces. There's only two of them, the empty thing, 1 point thing. They're the truth values. All right, those are the truth values, and this sits inside here. And well, I guess if you're really intense, you can go all the way down to -2, but that's just that's only truth and not false. This has true and false. This only has truth. And so, but it doesn't go further than that. It would go further than that if you had access to things like stable situation, but we're in an unstable situation. So it's just a kind of, it still works. Like all the facts that you prove kind of still work for these lower numbers. And so like when you talk about the connectivity of a map, you can talk about -1 or -2 connective maps. -2 connective maps are equivalences, and -1 connective maps are things that are inclusions on pi 0 and isomorphisms on all the higher pi i's. And so like all that stuff, all that language from homotopy theory works for these two negative numbers, but you can't go further. Am I answering your question? I'm worried that I'm not answering your question.
I understood that. I was just like, it was the sheaves that were throwing me off, not the
Oh.
not these definitions for spaces. But I understand.
Wait, -2 truncation though, it's just empty set valued sheaves, or like if you -2 truncate a sheaf, there's a unique -2 truncated sheaf.
There's a unique -2 truncated sheaf.
So why is that a useful notion to include, or is it not?
It's just useful for inductive definitions.
Okay.
Yeah. I'm not saying that the -2 thing is useful. I mean, the -1 thing I've been talking about because it feels normal to me now, but you don't have to believe in this part of the story to.
It's too far for me.
You feel like 2 is too far. Okay.
Yeah, I mean, it's only useful for formulating some definitions inductively where you make the like trivial thing like the -2, and then you say, oh, -1 means the diagonal satisfies the -2 property.
Yeah.
And 1 or 0 means the diagonal satisfies the -1 property.
Yeah, you have this little game that you play like that where you sort of you use the notion at the last level and then you say that the diagonal has that property and you sort of work your way up the tower like that. Yes, that's exactly right. Thank you. Yeah, so there's no -2 sheaves. If I take sheaves on a topological space and I look at the -1 truncated ones, then like really what I'm saying is I'm looking at sheaves, but I can only get point or empty set as the values of those sheaves. I can only get -1 truncated spaces as the values of those sheaves. And so that means that like, I have some opens that are they give me a point, and I have some opens that give me empty. And the opens that give me a point, I can union them all together, and that gives me a subset, an open subset. And so if I'm talking about sheaves on X and I'm talking about a -1 truncated thing, then it's really just specified by an open set, which is that isomorphism right there in words. Is it feeling better now? Was it George Mackey that said you never learn mathematics, you just get used to it? Now you just get used to this -1 business. Okay, so we have this adjunction here. It's not an equivalence of categories, but we are cutting out pieces of these categories where the unit and the co-unit are isomorphisms. And then you can check something. So this is where the exercise is. You can check something. So here we have topological spaces again. Here we have locales again. Here we have open. And here we have put. And here we have the full subcategory of sober spaces. And well, here's the full subcategory of spatial locales. And what you can notice is that this functor here actually lands in sober spaces. The points of any locale are automatically sober. That didn't have to happen, but it does happen. And similarly, the opens of any topological space are actually spatial. So what that means is that we actually end up with an equivalence of categories here between sober spaces and spatial locales. Go ahead.
That's fine. I got it.
And maybe just for good measure, I'm going to put Hausdorff spaces in here so that we understand this contains all Hausdorff spaces. Has more, a lot more. There's a risky topological space of any schemes in there. They're all sober. They're super non-Hausdorff, but they're all sober. In fact, that's why schemes are built the way they are. So for example, if you took take a complex analytic variety, so take a polynomial, have it cut out a subspace of C to the n, okay, with its usual topology, right? That and then topology, but now give it a coarser topology where the opens are the complements of the zeros of algebraic equations. Okay, but I'm only looking at the complex points. I'm only looking at this thing as a subset, but not a subspace anymore, of C to the n. And now what I'm giving you here is a recipe for soberification. You can sober up any space that you want. Right? If your space is drunk, you can take the locale of opens, you can take the points of that, and now it's sober. Would that alcohol work the same way? So if you do that to the example that I just gave, where I've cut out from C to the n some, say, locus of a polynomial equation, if you cut out that subthing and you perform this operation, then what you get is actually the scheme attached, the topological space, the scheme attached to that analytic or algebraic subset of C to the n. That's why the Zariski topology is the way it is. Right? You decided that you wanted, I mean, that's why you have to use all prime ideals rather than just the maximal. That's why the max spec is kind of crappy. It's because it's not really going to give you a sober space. But you can fix it, and when you fix it, you get the proper Zariski topology on all prime ideals. Okay, so what did we learn? We learned that if you're a sober topological space, for example, if you're Hausdorff, then you can be recovered from the category, in fact, the infinity category of sheaves on you, right? So what that says is that this operation, I've stopped in a couple of minutes. This operation, actually, wait, no, what is the timing?
Started at like 42.
Yeah.
And am I doing 50 minutes or an hour? 50 minutes. Okay, so I'm going to stop soon. So let me try and summarize what the point of all this is. So what's happening here is that I'm saying that you take a topological space and you extract from it this topos by means of the category of sheaves. And if I take this topos, I can reconstruct not the topological space, but a locale, but certain locales and certain topological spaces are basically the same. So as long as the topological space I start with is nice, in this case meaning sober, then I can recover it from this construction. Now, is that clear? I feel like I could have said that better. I'll try and say that better. Is it clear enough? Okay. All right. So, so this is kind of one extreme of the story that I want to tell. The first extreme of the story I want to tell is that if you take a topological space, then you can just reconstruct that topological space, at least up to soberification, from the topos of sheaves. So the question now is, what happens if you don't want to take all the sheaves? Remembering all the sheaves on a topological space is a potentially very big thing to have to do. There's a lot of sheaves out there. Maybe I only want to think about a certain class of sheaves, right? So for example, I could restrict attention to the locally constant sheaves on a topological space. And I'm going to tell you, I guess I'll tell you this in the next lecture. I'll tell you what the answer is in that case and what significance it has for, and then how to go further and go beyond locally constant to sort of slightly bigger categories. And then how to push this into sort of even more exotic topoi. And then maybe in the last lecture, we'll see how the timing goes, but maybe in the last lecture, I'll talk about how to try and move all of this into the realm of stable infinity categories. That'll come probably only in the last lecture, but we'll see. Okay, thank you.